First time.
I found a little surprising that you used to attend from the office. So what was the motivation to attend from the office?
After this class, I have tutoring. So
Oh, I
I
see.
pretty much get here and get some food and some coffee.
Oh, yeah.
So
I think someone else told me that, yeah.
I've been seeing you at the salad bar.
Right?
You what?
Yeah.
Oh, we like to go to the salad place.
Yeah. Okay.
And it's always interesting to, there's one lady that works there. I don't know how she doesn't get fired. Because
She's not.
no,
She doesn't use her gloves or what?
that clear container, like today, my salad had about, that much different distance between the top and the salad.
Uh-huh.
It was nicely full. She'll have that thing stacked that high and then she'll have to push the lid down.
Oh, yeah.
No, I think they do that. Everyone does that. It's not just one lady. I have been here for quite some time, and I don't know whether it's an instruction or they are just being very liberal about for the quantity. Yeah.
Yeah. Because I can get the small salad and still be pretty full.
Yeah, that's what I do. I
I
always
do a
I
small
always get
salad
the
and a
small
cup of
salad,
soup.
and I'm very satisfied.
I'm good until like 7 o'clock.
So,
There's one thing that, you can say.
and I was gonna,
Oh, go ahead.
I'm sorry, I didn't mean to
Oh, you're
interrupt you, Jordan.
No quiz.
Right,
Right.
so, but like, if we don't submit something on D2L, on the days that there aren't quizzes, then we still get like there's like, you still are supposed to submit something, right?
Yeah, that was what I said in the first semester. This semester, I'm going to just give everyone a chance.
Okay, cool.
I think
So
last
I don't need
semester
to
I
decide.
did that, and it was very hard to keep track because there are sometimes I had to give zeros for those who never attend or never submit quizzes, which there are some students like that. And then just because there was no quiz, they and so I was thinking, it's okay.
Gotcha, okay, all right, cool.
It's nice having number of people increasing in the rooms. I like that. Hopefully.
I did get the Dirac book you recommended.
Yeah, recommended, you did get it.
I have that.
Cool. But you've probably not got a chance to go through it.
I haven't yet. I'm going to this weekend.
Yeah.
But I also ordered the first volume of the Cohen book. So if there's anything useful for quantum mechanics out of that, I'll share.
Yeah, that'd be nice.
I have heard from many people that after, like sometimes what happens is that people study different textbooks and then go back and read Dirac's book. And Dirac is one of the first quantum mechanics book ever. One of the, I don't think it is the first, but he's surely the sort of the authority in that. And they always say that they get surprised as to how clear the contents are. And now, this is one of the persons from recently said, and they also realize how much complicated other textbooks make it in the hope for making it clear for younger people. So that was a comment, not from by me, someone else. So take it with the pinch of salt. But I think I sort of probably agree to that. Yeah.
When Feynman, because I've been listening to those lectures, Jordan, you were kind of an inspiration.
Oh, I was? Oh,
The day that you just listened to the lecture because you were doing the clearing out the basement,
Oh yes.
and you were talking about how it really was helpful.
yeah.
So I got Audible and I downloaded some of the Feynman lectures and just listened to those because, it just, I can kind of soak that in. But he was talking about the Dirac notation. He actually had a lecture where he told the students, he said, we're going to do something fun today. So if you want to leave, you can just leave. I'm not going to mark you absent. And he was talking about that notation during the lecture. And, saying, don't run away scared.
Interesting.
So you recommend the Dirac book?
Dr. Sujesh recommended it. It's an inexpensive book. You can get it, and you can even get it on Archive, I think, archive.org. I got it ended up, it was a paperback. It was supposed to be a hardback, but it's only like that thick. But you can get it for $35.
And what's it called?
It's Dirac's Introduction to Quantum Mechanics or
I
something like.
think it's just, yeah, introduction.
It was published in like 1933 or something.
31 or 33, yeah. 31, 33, yeah. 33 probably, yeah.
I've said this
Um,
before, but I think sometimes I get more out of those older books. It seems like they're more like direct and to the point, whereas some of the newer books, like there's so many people competing for like the same market that they just try to like ego stroke a little bit to make their book feel a little bit better, or just add a bunch of information that it maybe isn't necessary and gets
Or
confusing.
editors who don't actually understand physics, but they're just trying to give a pretty product.
Yeah.
I've got a friend who published a few books and he hates it.
Yeah. Like, it's not the case for every book for sure. Like sometimes as time goes, you have better ways of presenting it. You learn better notations and surely things simplify a lot. Like calculus is a classic example, right? With the derivative, just that notation, if Newton did not use that, you get much better. You're more efficient. Maxwell did not use our vector calculus notations, and we are better off that way. But I think quantum mechanics, I think, is where probably Dirac's book still holds a lot of strength. And again, that's my thought. And I some of the friends I have, they do think like that. It doesn't mean that the other books are not good. It's just Dirac is still good. That's it. So you can okay, so let's see. Oh, I was supposed to set this up. Yeah, you guys keep chatting for some more. I have to do this. Oh, where is Aliyah? 1, 2, 3, 4. 5. So I was thinking of having midterm 2 in class. Compulsorily, like Jordan, can you do it?
I can probably do it, but the way my schedule's set up, as soon as the lecture ends, like at 3 o'clock, or not 3.
But one day, can you make it?
I think I can make that happen for sure.
I'm good.
Just have to take off work that day, but I would need to know like.
Would it be okay if I demand it?
Yeah, I think you could demand it, but again, like I said, you'll have to let me know ahead of time.
Yeah. The date will be fixed. I mean, the same date. It's just that I'm going to.
Because I'll lose like a day's pay or whatever for that, so I'll need to like make that up.
Because I made that because I saw you in the corridor the other day. Oh, Jordan is coming. So,
yeah, every Friday. My schedule's tight, but I can make it work. So.
Yeah, it is okay. Yeah, it's only one midterm, right? After that, there is a final. A final, I might be more liberal.
Okay.
But let's have this. So I did grade your midterms and I posted the grades. So by any chance, did anyone get a chance to look at it?
Yes, I saw that you posted it.
Yeah, most of you did well. So there's a homework I posted. this has a small fee for quantum mechanics that maybe since you guys keep mentioning, it might be nice to connect with it. I don't use these are all in operator forms, no bracket there yet, but just think of it as operators, but it gives you a feel for what quantum mechanics, how do you connect quantum mechanics and classical mechanics. So hopefully helpful. Midterm 2. This is on March 30th, Tuesday. This will be in class. No Zoom. So, I think Rob and Jordan and earlier, I think they are the ones who should be considered. I think, but Rob always comes. Jordan will be the one who will have to compromise one day of his work. You will lose your salary, 1 day salary, Jordan. And Aliyah does come. I mean, yeah, she tries to avoid because of her kids, but I think she does come once in a while. So I think 1 day it should be okay. Unless things change, like if we go in the last week of March, if we see that COVID statistics are completely out of off from where we are now, then we reconsider. But as of now, that's what it is. Okay. So with that clause, that
Now, is this one that we can complete within the class period?
yes. So this will be about 3 questions, but reasonably elementary. And that's basically because I like the work that you guys submitted for midterm 1. I was actually, even the homework, I'm kind of happy that you guys are using the legendary polynomials you studied last semester, and most of you were efficient with it. So I liked all that. But there were some silly mistakes that was being made, which I feel are not acceptable at this stage. So like I cannot, certain things you cannot, like background is something I cannot fix, but I can always make an assessment of all that so that those of you are having that problem at least know that you have that problem. That's the best I can do. So that is a simple purpose. But overall, I think I'm pretty satisfied with the way it is going. So yeah, so here are the scores. So we can go to here. So the highest, this is including midterm 1 homework, everything. And I have been hard in grading to a certain extent, or I would say to a good extent. So that's 93, 83. So that's the raw score out of 100 homework plus midterm. And then we have this, what is this called? We call it quiz, right? Yeah, quiz. And this is 0.818. And then you curve this, right? So the curve is, remember, whatever, let's suppose I were to call this T total, T plus I give back whatever you lost, right? That's your C. But if I give everything back, then you get 100, everyone gets 100. But instead that's scaled by how much you score in your quiz. And I also, or I return back certain percentage, but how much you get out of that percentage is dependent on your quiz. So I return back 20% of whatever you lost. Based on that, this is 98. So so this is 80. Basically, it chose this so that this falls in an 80, and that's an A, and that's B. So that's a boundary for A and B. And overall, it also happens that think the top 3 students have been, at least from what I see on the paper, have been at least critically thinking about the problem, it seems to me, on the paper. You guys might be thinking, and I will never know because you don't write it. So excluding that conclusion, I feel, think more or read more about what's going on. It's not just the problem and doing the problem. You have to think critical. So that's fine. Hopefully that's useful. I remember assessment always has this, what do you say? It's personal. It need not be the conclusion. But hopefully make some useful conclusion out of that. Okay, that's all. Any comments or anything? Okay, we want to slightly change gears a bit, but we still want to do magnetism for some more time, but let's do a little non-trivial part of the magnetism. Let's talk about magnetic energy. So remember, typically force is connected to energy. What's the connection between the two? Typically, it's potential energy. What's the connection usually? What's the equation that connects potential energy and force?
It's the product of force and distance.
That's actually correct. Let's make it a little better.
Integrate the force over the change of distance.
Yes, that's how about that? Yeah, that's correct. That's pretty much the same as what Rob said.
Yeah.
But let's make it, that is an integral, remember Maxwell's equation can be written in integral form and differential form. So in differential form, what's the connection?
Minus gradient.
Yeah, minus force is a gradient of energy, right? So you would say force is negative gradient of potential energy, right? It means that the system is trying to minimize the energy, and remember slope represents the gradient, and if it is negative gradient, that means it is a minimum. Otherwise, it's trying to maximum if it was a positive. So force is a manifestation of the system, or the system's manifestation of the fact. It's trying to minimize its energy. In that way, what is electric field? So electric field, let's say, is connected to the electric potential, right? It seems like it is just dividing out by the charge Q, right? If you have a force divided out by charge Q, then it is the electric field. But it's more than that in the sense that it suggests that a small, infinitely small element of space actually has energy content in it if there is a electric field around it. Right? So electric field square, remember energy is proportional to electric field square. I think electric field, energy density is that, remember, is half epsilon E squared, right? And magnetic energy similarly is half mu naught E squared. So just because electric field exists, even without the other charge existing, or for that matter, even if the charges are extremely far away, but if there is a volume of space which has electric field, there's energy associated. So it's much more physical than what we think. It is not an intermediate mathematical step where to understand force. So this equation will be equal to here. Anyone? Electric field and electric potential are connected by?
Use the negative gradient of the scalar potential.
It's scalar potential, correct? Right. So that's good. And we have a feel for this kind of like think of gravity again, right? Yeah, let me use gravity.
Shouldn't you also include the potential of the magnetic potential minus the magnetic?
Yes, yes, that's what I'm coming to. Okay, give me a few minutes, maybe. So this is electrostat. So we are still doing statics, right? Yeah, that's what I'm motivating this to. So of course we have a gravity also, right? If there was gravitational field, then we have gravitational potential, gravitational field, gravitational potential. And here we can say, we typically write just this one, G is equal to negative gradient of phi. This is the acceleration due to gravity if you want, but more appropriately, this is best written as G M over R square times R hat is equal to negative gradient of the potential energy, which is G, or potential, which is Gm over R. And actually, this has to be negative because gravity is attractive. That's pretty much identical to electrostatics in here. And all this leads to the idea, whatever Jordan was pointing out. What about magnetic field and what is magnetic potential? Or magnetic potential energy, right? And by the way, what is the conclusion? This is the mathematical relation between these two. What are the physical consequences of this fact? If force is a negative gradient of energy, what are the consequences? First of all, or maybe before that, can you think of anything, any other place where you see this? Force is related to the negative gradient of energy? Any other place? Does every force satisfy this? It does not, right? Moses says it does not. So only fundamental forces, very like gravity, electrostatics. We'll talk about magnetostatics. This is slightly crazy in a sense. There was this harmonic oscillator also does the same job, but most of the time forces are dissipative. Like if it doesn't satisfy this, that means you're losing some energy. So all the changing energy is not showing up in the force that we are seeing. It is
Conservative forces.
Yes.
Defined in beginning physics.
exactly. So this is what's the idea of a conservative force. Yes, that's exactly the word. If this is a conservative force, that means the consequences are that first of all, it can be so if it is a conservative force, del cross F is 0. That's one thing. Second is that if you go around a loop, so if you go from here, go all the way to another galaxy and come back, your change in potential energy is the same. Gravitational potential energy is the same. You can go whichever path you want. While going, you go visit one galaxy, and while coming back, you visit another galaxy. But as far as you reach home, your potential gravitational potential energy is 0. So that's typically written as TL dotted with F is equal to 0. So that's your three sort of ways of writing this force is gradient of potential energy or the work done. So this is the work done. If you go around a circular path, that's equal to 0. That means whatever you gain, or whatever you lose, you gain when you go back in the same path. And the cross product of forces 0. All this is very compactly said, as Rob said, that this is these are conservative forces. And that raises the question, is the magnetic force a conservative force or not? Right? If it is, there must be a potential energy associated with it. What's the potential energy? Is there a magnetic potential? We have been calling something a magnetic potential, but in what sense can we think of a potential energy like this? So that's the question we want to ask. Let's begin with the work done. That's actually the easiest, and that's the most popularly stated quantity. And let's ask, what's the work done by the magnetic force? Remember, maybe we should work that. What is the magnetic force? We know is QV cross B. So force, if there is no electric field, it is Q times velocity cross the magnetic field. It doesn't have to be uniform. Any magnetic field is equal. It's always true. So the work done by this force, work is always defined as the work done by a force. Right? That's the difference between the quantity we think of work in colloquial language. This is the work done by the force F. So that's defined as dL dotted with the force F. So, right. But this is not in general a unique relation. If you go from here to there or here to there, the path matters. So let's go from position 1, so R1 to position R2. You know, three-dimensional space, that would be vectors, right? We're going from 1 to 2, and we have to specify the path also. All that is necessary when you're defining the work, unless it's a conservative force. As of now, we don't know that. So if we substitute this, and now let's say how do we calculate work done? Yes. So what is dL there? So we are actually making the charge or the mass move along that path, right? So that's dL. And that means it is also the change in position of the particle. If we are actually, the particle is moving around that, so that's also a change in position of the particle. And remember, V in that case would be equal to dL by dt. Change in position, if you divide it by the time it took, that's a definition of velocity, if you want. And then we learn that this is R1 to R2 along a path, and we have dL, which is at least directionally. So you notice dt, one might wonder, oh, what's the direction of this? What's the connection between them? Always go into the limit form, and it might help you to gather what's that direction. The direction of delta L is exactly the same as V, which is not very surprising, right? I mean, we have done enough of mechanics. That should be there. So this is Q, and you pull out the Q, and that is dL by dt crossed with B. And directionally, just by directions, dL cross B will be perpendicular to both dL and the magnetic field. And if you dot it with dL, that has to be 0. So every small displacement that you make because of this vectorial or the cross product nature of this force, this is always 0. This is slightly more than what we say in the definition of a conservative force. In the conservative force, we say that in a small path of the curve, it might not be 0, but when you come back, it becomes 0. Here we are saying that at every step it is 0. So of course it will add up to 0. So it's I'm not saying that this doesn't mean that this is conservative or not conservative, but this is a bigger statement than what a conservative force equation is. So let us, so this fact does not imply that there will be a potential energy associated with it. And we can write force as a gradient of of some quantity. In fact, it turns out that it is not just a potential energy you can associate with it. Yes, there is a potential energy you can associate with magnetism, but there is something more to it. There is also a momentum. The take-home message in this whole is going to be that when you're talking about electric field or gravitational force, there is a potential energy, but magnetic field also changes the momentum of the particle. So there is a just because there is a magnetic field, the way you define momentum has to be different. And that has to go back to now, how do we define momentum? What's the connection between momentum and energy and force and all that? Is it just a convenient definition that E is equal to mv, which it seems like, right? When we're doing mechanics, the only equation is Newton's law, F is equal to ma, and it our derivative of momentum is equal to the force, and we say that, okay, that P there sitting there, so it is mass times velocity. Is there a situation where momentum is not really mass times velocity? Is there a situation, by the way? Are you guys familiar? Is it always mass times velocity?
Like for photons.
Yes, that is true, but that is too far. Let's do something simpler. I was just doing maybe connected with Lagrangian, like what's the connection between Lagrangian and the momentum? Have you guys taken classical mechanics, some form of classical mechanics here or there? So the idea is that whenever you're doing Newton's laws, it is possible to define what is called a generalized momentum and a generalized generalized force. The easiest way to look at it is torque is nothing but a force associated with an angular variable. It will be called a generalized force. Right here, we are changing with respect to position, so force is equal to negative gradient of potential energy. So notice energy is the central piece. Change in energy of any kind will appear as force. So this is with respect to position. I change it with respect to angle, and that would be the torque. So in that sense, this is a generalized force. So torque is nothing but a generalized force, but torque is actually a vector. So now if I can define a change in the angle as a vector quantity, which is what we do typically, you take an axis and there is a magnitude associated with that. Let's say making it more complete if you want, but in very simple terms, change in energy with angle is a torque. And then the question is, what is the momentum associated with it? Okay, if there is a force, we associate momentum. In the torque scenario, what is the momentum? What is the momentum in generalized momentum, if you want? The way force is connected to torque, what is the connection between momentum and the angular quantity associated with momentum? Is the question clear?
You're talking about the inertia times d theta dt.
Exactly. I think there's a one-to-one correspondence, right? But m times v, m goes into I, and v goes into omega. Very good, right? So that's your momentum. Then this is your generalized momentum. But these are all. This is the spirit in which we want to do this. So what is the momentum in this scenario? So let's do a little bit of Lagrangian. I mean, even though I haven't done any of the Lagrangian here, but assuming that there is some form of classical mechanics you've taken, but I'll do it in a spirit where it will be complete in itself. Okay, so let's try to start from this force equation and see, can we identify what is the energy associated with what is the magnetic energy and what is the magnetic momentum, if you want. Then we will start from force is equal to QV cross B, but I want to make it very specific. When I say force, I mean this, at least the way it is appearing here. It is change in momentum. Since we are going to change the definition of momentum itself, so let's be very clear. We are beginning from mv. That's q v cross v. This equation itself is very interesting. You should pay attention to that. Notice that we are saying if change in the vector, forget about the meaning of the quantity, change in the vector is equal to v crossed with some vector, right? So let's call it omega, right? That's q times b over m, I've called that omega. Right? Where else do you see this equation? It's a very common equation everywhere you will see. Or what will be the consequence of this equation? If there was a quantity v, does it have to be velocity, is equal to v cross omega, where omega is a constant, let's say for the time being. What will happen to, what will be the physical consequence of that? What will happen to v as an evolution in time?
It'll go in a loop. Or-
That's correct, but something more, yeah. Notice there is a, yeah.
Is it just a rotation?
Yeah, that's very similar to what Moses said. Something more than that. So notice omega is a constant vector. Right? Something like gravity for, and gravity in the upward direction. I think we can always twist it the other way. And now there is another vector v, right? It doesn't have to be gravity. I'm just telling. So there's another vector v, right? Now what does it say? Like what? This is of course constant. I mean, what is the motion of v? That's what we're saying. Some vector. Right? So in time, it's going to change. How is it going to change according to that equation? So this is the equation of precision.
It'd be like,
Oh yeah, you were, sorry.
well, I was just saying that if the change in velocity with time is equal to the cross product, that means that it's changing in a direction perpendicular to v.
Hmm.
So the first I was thinking about a charge in a magnetic field.
That's correct. That is correct, charge in a magnet, but I was trying to make it very general.
Okay.
Like there it is, like you're being very specific, oh, this is a magnetic field, then we have an intuition of a charge. But let's say any vector, this could be the spin, for example. In quantum mechanics, this comes exactly the same equation comes in the context of spin. Same thing, it can be the precision of mercury, for example. There it will come out the same, but then the context completely changes. It is precision about, there's already a rotation going on. It's much more geometrically complicated, but any vector, I'm saying, like get rid of that intuition out and a mathematical equation or top, right? We have a top, symmetric top. When it goes around, that's gravity. Like if you put this down, symmetric top obeys this equation. The L, angular momentum, is equal to L crossed with, there is some gravity coming here, but probably there is some constant here. Like dimensionally, I might not be right because G doesn't have the dimension of 1 over T, but some constant here, and it also precesses around, and it's the same equation. You will be able to write the top equations of motion in this form. Probably negative because there might be a negative sign because the gravity is pointing downward. I'm not sure, but except for those C, which I can absorb the negative sign. So what will happen is that this will go around in a circle, right? And this will remain fixed. That will stay fixed, and this will precess around that point. This is what a spin does, right? When a magnetic moment, a spin is nothing but a magnetic angular momentum going in. Motion of angular momentum is basically motion of a spin. So it goes around. It might be going, having a linear motion also, but we'll have this also. Okay, but that's going that was a digression. So we have this equation, right? That's our equation of motion in a not necessarily a uniform magnetic field. I'm not assuming it's a uniform magnetic field. All right. Actually, since we are doing this, let's put an electric field also. Why not? Right. So the complete equation would be Q times electric field plus Q times V cross B. Let's put the electric field in there also. And the idea is, again, force is negative gradient of potential energy. How best can I do that? Is it possible or not? So let's bring in the definition of electric field in here. So electric field is equal to negative gradient of electric potential, the scalar potential, and that is minus of dA by dt, the partial derivative of the vector potential. And that's what I think Jordan was trying to put right in the beginning. What about B? Magnetic field is the curl of, and all these are, at this point, I have stopped using statics just temporarily here, but I'll impose it again whenever we want simplicity in that. Right, so this is very general at this point. And then we have d by dt of mass times velocity is equal to, let's collect the gradient as much as we can. So this is minus gradient of q times phi. That's this term. And that is minus time derivative of q times a. That's, and I have plus q v crossed with tau crossed with a. V, remember, is the velocity of the particle. Velocity of a particle does not depend on the general variable. Like gradient doesn't operate on velocity. It appears only on one point. Okay, so let's expand this out. Okay, so this is d by dt, and seeing some of the things like this doesn't have a gradient in it, right? Whatever has a gradient, I'll keep it on the right hand side. And whatever does not have a gradient, my hope is that it will actually, I already revealed that that's something with momentum going on. So I'll take it to the left hand side. So this is mv, and there's plus d by dt q times a. But notice one is partial derivative, one is total derivative, right? The derivative of momentum in the Newton's law is the total derivative, which means that what's the difference between total and partial? If there is a functional form, the total derivative will know the presence of an implicit dependence in time. For example, position implicitly depends on time, but explicitly doesn't have any form. But this one looks only at the functional form, like actual time dependence in the function. Okay. So this is minus gradient of q times phi. And we have the cross products there. So let's expand that out. And it is q times v. That is the first center vector is the free quantity, right? And this is a. But this can act only on this. So this is dotted, right? Is that notation clear? I've used this before also. These two vectors are dotted, but the gradient is a free vector, and this acts only on A. I will be able to change this better because we actually can enter the gradient. Gradient does not operate on V, so I can actually take the V inside. But just to make it very clear, this is how it shows up in the first place. Oh, there's a plus, not minus. Plus and minus. The second vector is decided by the by A, and the rest of the quantity is dotted. So that's easy to write. So that's V dotted with gradient. So the gradient is acting on the third vector, but it is vectorially dotted with the first vector. So it is this is a directional derivative, if you will. Okay. Oh, there. Yeah. So let me write this again once. So two things. So this is Q times phi. Notice V can enter the gradient because velocity is the property of a particle, right? It doesn't depend on space variables. So this can enter in here. So this becomes a gradient. And that's Q times V dotted with A. Now I don't need that arrow representing that these are the two quantities. And you see, that seems like a magnetic energy, right? If this is electric energy, that must be magnetic energy. But there are lots of other pieces that are showing up, so it's not a pure energy that's coming up. And there is one more piece in here, which I will write as minus V dotted with gradient and Q times A. So whatever shows up as total gradient, I'll keep it on the right, I said, and I'll take the rest on the left. So I have time derivative of mv. And there is this operator, which can be thought of as partial derivative with time, and bring out this v dot, the directional derivative, onto the left side, acting on Q times A. It's equal to negative gradient. So whatever shows up as negative gradient is my energy if the left hand side is the force. So this is Q times phi minus Q times V A. Okay. Oops. Any questions until now? Probably simple. Each step is straightforward, I think. Now, I would like you guys to know what this operator should remind you of something. What is that? If you've done fluid dynamics, that's the first thing you begin with. But what is that operator in your partial derivative course? No?
Which is the full total derivative.
Very good, very good. It's very good. So if you have a function f, let's say x of t, so this is implicit. This is implicit. That's it. What Jordan is saying is that this is nothing but total derivative d by dt. That's it. But how do you see that? If that is an implicit dependence and an explicit dependence, right? So if I were to take a total derivative of this, there are two places I can hit. Either I hit here or there. So the explicit one is what you write as partial derivative with time. That hits the second t here. And the first one, I have to use a chain rule to reach that. Right? So first I will differentiate with respect to x. And then I have to differentiate with respect to x. This is for a one variable. If this was a three variable quantity, which is like a vector, then this becomes the velocity dotted with the gradient. This is the velocity, that's a gradient in 3 dimensions. So that's velocity dotted with gradient, and it's not a scalar function. This is acting on a vector function. Those are all generalizations, but this is the simple concept. And this is what you will do if you ever do a bit of fluid dynamics. So you have a fluid that is flowing through, and you want and each point has a velocity in that. You want to write things in terms of velocity. So then that's the first quantity you will see. And but that's a good observation. Okay, any questions there on why that is the total derivative?
What is the
X, this is X.
oh, okay.
X. So usually you would say it this way, right? I think function derivative with respect to X, I think this is how mathematics. But I wanted to write it the other way so that you see the velocity. You do the chain rule. First do it with X, then X with T. But I wrote it in the first step twice just to identify with what we have. Or this also shows up in thermodynamics, right? All those partial derivative, wherever you see partial derivative. Okay, clear, very clear, Christian?
Yeah.
You want
I
to
don't
ask?
know, maybe I'm being silly, but it's not clear to me why those terms are summed.
Those
Partial
terms.
F, partial T plus, I don't know, I think I'm probably just,
Why? Because we'll have to do a Taylor expansion. Let's do it. Isn't that how you do it? Okay, so let's see. I think so. That's how I would convince myself. Okay. So the question is, why is it being added, right? So we have a function f, f of, let me write t first, and x of t. So let's say this is always fine. And now I want to find derivative, right? The f by dt. By definition, my derivative would be limit delta t tends to 0 of f of t plus delta t minus of f of t divided by delta t. But that should be fine. So I'll change both places there. This will be, and then I'll do Taylor expansion. It's kind of going in circles, but I think it should help you. So this is f of, oh, what do you mean? What do I mean by this? I think I should make it more explicit, correct? So this is x of t plus delta t. Reasonable? Right. So this is, now we Taylor expand, right? So we say that this is all small. So first I expand x. So this is x as a function of t plus delta t times dx by dt. Is that okay? And there are higher order terms, but I'm not going to keep them. Minus f of t. Oh, this is also t comma x. Right. And now I expand this whole quantity. This is, maybe I'm using the definition itself, definition of limit in proving the limit. So in a sense, it might not be perfect proof. So now I again expand. So this is f of t comma xt. That's the first term. This can contribute or this can contribute, right? So plus delta t, but this one is a derivative with respect to t. So this is the f by dt. And the second one is delta t times dx by dt times partial derivative of f with respect to x, like x in the sense that's the second variable. And that is minus of f already there. So in the limit delta t tends to 0, right? First of all, these two cancel out. And this exactly cancels out. There are other terms here, delta t squared, right? Order delta t squared. Right? But they will all go to 0. It's not an approximation, they will all go to 0 exactly. So what is left out is this sum of two terms. Is that convincing? Okay.
so then is the definition of a partial derivative where you would just say it's like f of t plus delta t comma x minus.
Again?
So essentially just like you change the explicit time dependence by delta t and without changing
That's correct.
and keep x.
That's
Okay.
correct. That's correct. Yeah,
I
that's the partial derivative. And if it's a single variable like x here, this should be partial derivative, but I wrote dx by dt, but that's only one variable. It doesn't matter what it is. So in that case, you're free to write whatever you want. But otherwise, this is what I mean by the partial derivative. This becomes crucial when you're doing Lagrangian mechanics, where implicit time and explicit time plays a different role. Okay, I think that's reasonable. Okay.
Yeah, thank you.
Okay, good. Okay. But let's go back here. So good observation that this is a total time derivative. And then we have, this is d by dt of mv plus q times a. Right, that's equal to negative gradient of q times phi minus q times v. Okay. Good. We did find a gradient of something, but at the price of changing what the left-hand side is. So what our idea would be to change the definition of momentum, change the definition of energy, both. So it doesn't come at a single so momentum now, this is a generalized momentum. So T is equal to mass times velocity. That's the classic definition. But now there is a contribution just because there is magnetic field. Think of circular motion again, like when you put a magnetic field, things change, right? Its momentum is changing, its energy is not changing, right? Half mv squared, the kinetic energy remains the same, but its momentum is changing because it's changing its direction. So that's that momentum changing, and potential energy of the charge of the mass that has the charge is equal to q times phi minus q times v dotted with a. Okay. So the names here, let's say this is the this is called the canonical momentum. That's very standard. Canonical momentum. Best is now I have to give it some name. Let's call it kinetic momentum, maybe. This is not standard, so feel free to change whatever you want. Kinetic momentum, maybe then q times say magnetic momentum. Is that a name? I don't know. Yeah. Potential momentum. I call it potential momentum. This is okay. Like I don't recall this being called potential momentum, but I'm calling that. So be very critical when you're reading other books. Like, this is very local. Inside these four walls, we can use it and everyone understands. Okay, and this is potential energy. This is electric energy, which is standard, like voltage. When you apply voltage, charge moves, that's that energy. And this is magnetic energy. Okay. And remember that positive and negative sign in energy is very crucial, right? Electrostatic energy is positive. gravitational potential energy is negative. Gravity is attractive. Electrostatics is repulsive. Two positive charges repel, two masses, which are always positive, attract. So
those are
what
both
does this mean?
electrostatic and magnetostatic energies, right? Not just
Oh no, at this point, this is everything. This is whole of electromagnetism. I didn't use any approximate notice, except maybe quantum electromagnetism. I didn't use the quantum features in there. This is the classical electromagnetism, but no, I haven't used any time. I kept the time dependency, right? Like when you identified that this is a total derivative, that's taking care of the time dependence. But it is true that this piece alone, if you were to go to statics, you will lose this and have this. But probably that's not completely accurate enough. Like there might be flaws in that thought process. If you were to work with statics and then just deal with this, you might miss some part of, you might not conserve things.
I was just thinking like each one of those pieces itself, like Q times the potential is electrostatic energy minus the
That's correct.
magnetic energy.
This is what we are going to call it magnetic energy, yes. But the question you are probably asking is that can you have this magnetic energy in statics, right? That's your point. Agree?
Yeah.
In statics, would it be okay to say that? Let me not answer that question. I don't know about that.
Okay.
Like I'm afraid that if you keep only this and not this, you might lose some. You're not conserving things properly. I'm worried about that. But then remember that whatever we did magnetostatics, there was a static current and there was a field that was static. We did not bring in another charge that interacts with that magnetic field. This was a one-way process we did. We have to bring in two loops of current and make it interact. Only then we talk about energy. All the problems we did was there is a current loop, it creates a magnetic field. That's it. We didn't talk about what that magnetic field does to something. And when it does something to that, then it will move. And I expect that if you want everything to be balancing in the equation, then you need to have that. But I'm not very, I don't want to stress on that too much. Okay. Is that clear, Jordan? Did I at least? Okay. Okay. But I said that usually negative sign has meaning, significant meaning. Gravity is attractive. Electrostatics is repulsive. There's a negative sign here. What does that mean? Like, does that mean that magnetostatics or magnetism is repulsive? In what sense is it repulsive if it is? It is surely repulsive because it has a negative sign in that. Magnetic or magnetic phenomena, if I were to call that, apparently is repulsive in the sense that gravity is attractive and electrostatic is repulsive. Sorry, magnetic phenomena is attractive because of the negative sign. I said it wrong. So in what sense is it? And you have seen this before. Based on the magnetism that you are familiar with, in what sense is magnetic phenomena attractive? This is stated very, in introductory physics, we stated, not in this language, but not in this context.
Opposite poles attract each other.
Opposite poles, you went too far.
Okay.
Opposite poles attract, but then opposite charges also attract, right?
Mhm.
So apparently this is different from electrostatics. But you, like the sentence that you said, very similar actually, think. But if you think in terms of opposite poles, they are exactly like north and south pole attract, positive and negative charges attract. But there is something in magnetism which is opposite of what we are saying. Like charges repel in electrostatics and What happens in magnetism? Like quantities attract. Is there a statement like that in magnetism? No? Okay. Like currents? What do like currents do? Is that familiar knowledge? Like current, what do I mean by like currents?
Like parallel wires.
Parallel wires, yeah. What happens to parallel wires in magnetism? Like currents attract or repel? Like attract, right? Like currents attract, like unlike currents repel. That's the statement. Remember, Q times V is current, right? And so how do I see this? How do we see this? So let's elaborate on that a little. It should be possible. And your homework is associated. No, your homework is not associated with that. Oh, I'll do that in the class. I changed the homework. I was thinking of doing that as the homework, but then I made some quantum mechanics. Yeah, okay. So, in what sense is that meaning like currents? So, let's call this U of t. Is this readable, Jordan?
Yes.
Okay. So this is it. Notice what is happening here. Always potential energy deals with two quantities, right? So this is a field or magnetic potential produced by one charge, and this is, let's call this V1, Q1, and this is produced by another charge, right? Produced by Q2, V2. It has to be moving, so we cannot just call it charge, a moving charge. So this is moving charge. Right? So a moving charge produces a magnetic potential. It interacts with another moving charge, and that's your potential energy current. Right? But we know that charge times velocity is current that can be written in terms of current density. Right? So Q1 times V1 is the same as d cube r in a small volume element. Think of this as a compressed into small particle. And then this is current density, if you want r prime. Correct? Great. So that's the same idea. And J itself is given in terms of rho. So potential energy then is equal to negative. I can write this as an integral d cube r prime times J1 now. Let's call it 1 r prime dotted with the electric potential due to 2. I should differentiate that at r prime. Actually, let me say this is r. Sorry. Till now we have been using r prime, but let's say this is r. Or maybe better, right? Let's say this is 1. So this is at the position of charge 1. So electric potential at the position of charge 1 is what matters. Like, I don't care for where the electric potential everywhere is, but at the position of charge 1. And let's call this 1, 2, right? Interaction energy between 1, 2, the magnetic potential energy due to the interaction between the two moving charges 1 and 2. Is that very clear how I went from there to there? It's a leap, but it's just a mathematical leap. Like the concept is there, and then it is just going into the elaborate formalism. Okay, but we know the electric potential now. Let's put that in. This is minus dqr1, J1, R1 dotted with this we know is mu naught over 4 pi. I integrate over where I'm scanning for the other charge, right? R2, so I have to scan the whole space for that. So it's d cube R2. and this is J2. And the observation point is now R1 because that's where the charge is, and this is R1 minus R2. So this is equal to minus mu naught over 4 pi E cube R1 E cube R2, and that is dot product of J1 dotted with J2 R2. So that's your interaction energy, and we will use this for very simple scenarios. I want to do this in a little detail, so I'll come back and do that instead of doing it now. So I'll start with two parallel lines. We do know this, right? This is a classic example. We always do first create the magnetic field due to this, and then do the opposite, and we'll get this. And we will also define. Remember, whenever you have a magnetic or electric energy, immediately you define what is capacitance, right? That's a very connected concept. Between any two objects, you can define a capacitor. Like capacitor need not be parallel. That's the simplest capacitor you can think of is a parallel capacitor, but any two objects has a capacitance associated with it. So this quantity in between is, you can pull out the capacitance of the geometry. Similarly, here we will introduce what is called the inductance in the same way and talk about. And here itself, we can already see, right, there are lots of things you can do. We always talk about parallel wires. You can make it an angle, right? You can make it perpendicular and all that. So this is a very general scenario. We won't explore too much there, but I will do on some simple scenarios and do the classic problem. Yeah, I did not give this as a homework. I think earlier I have given this as a homework. So I was thinking of giving this. I'm thinking this was not, this didn't show up in the exam or anything. Right? Seems very familiar. I've seen this, but I think I was just looking at it. But I'll stop here and we'll come back to this so that we have the whole thing together in the next class. Okay.
So can you combine these J's somehow in order to do this in like a?
Yeah, I mean, combine this J's, maybe, so this is, okay, what is J, right? J1 here is, R1, let's say, is Z hat, right? It could be the current I1, and it could be on the axis, let's say X1, X minus 0, and Y minus 0, right? That's on the axis. Sorry, on the Z axis. So that's your X, that's your Y, that's your current I1. And J2 could be, that's the simple scenario we do. Z hat times the current I2. It could be in the opposite direction, remember, it could have been minus the quantity. And now I move this. So let's say this is A. So this is delta of X minus A. Delta of Y, I keep it still 0. Right? That's a simple configuration you can have. Is that your question?
Yes, I was just thinking like, is there a way to make this just a single integral instead of doing?
No. Interaction energies always will have two. Remember your potential energy also, if you were doing electrostatics, you have to scan for both charges. In fact, that's where you see that if you were to do this and scan both, and don't differentiate the fact that there is only interaction between 1 and 2. And suddenly you will see if you don't differentiate that, one interact with one itself. That's a question. Right. And Maxwell began this, like he said, self-inductance. Right? We even see this in introductory physics. We call it self-inductance. Like if you have an inductance loop, does it have an inductance of its own? And Usually not, they're divergent quantities, but sometimes you can make sense out of it. Sometimes, I don't know, or I've been saying anything. Can you make sense of, it's like sitting on a chair and lifting that, right? That's what type is. So it's not very, logically very strange. How can you exert a force on this? But remember all this quantum effects, right? I mean, there's in between, you can interact with something and then come back, and in that form is possible. But let's go there. Yeah, we'll see. I'll at least find them out. Okay. Okay. Okay, I'll stop here. Yeah. So even though I can take extra time, but I think I shouldn't use it all the time. Yeah. I think we caught up a good bit because you guys allowed me to use this extra time. And whenever needed, I'll take it again out. Good. So this is good to have 4 people. Is this a limit? No, we are still, we can have one more person inside.
Yeah, so are we going to have to find a different room for the exam? Or
Oh, I will get out. Right? I'll stay out. Yeah. Yeah, good point actually. Yeah. Yeah, so you guys will be here, I'll stand there, distribute it, and then you take the exam, I'll go back to office. And yeah, be honest, that's all. I don't have issues with that. Yeah, things you guys are fine. It's just to make you guys do it in a spot. That's also part of it. But most of you guys are doing good. I don't expect any issues with that. So I'll make it very simple. Oh, that is what probably sometimes gets challenging, is that it will be too simple. And then sometimes it's easy to make mistakes. You've done all this hard things. Like what I usually like to ask is something on Gauss's law, right? Which is introductory level, Gauss's law, Ampere's law. Like now we are doing magnetism, something very which we use it in almost the first few steps of the derivation. Yeah, something like that. So, yeah, don't get overwhelmed. Just keep doing your homework. That will be necessary. Okay, good. And blame it on Jordan because he showed up. I saw him in the corridor and Jordan is here, so we can now have an assessment.
Now he'll be afraid to show up again.
It's pretty specific the days that I can be there and can't be there, but
Yeah. So try to arrange it, okay? Jordan. So
yeah, I
since,
think it's far enough ahead. I can make it. I can make it happen.
Yeah.
No problem.
Okay. Okay, Jordan. Yeah, maybe I should put the camera up so that you can. Oh, he left. I was moving the camera for him. Where is he? Okay.
He showed us.